All right, let's finish up 1.3 day 2. The goal for today, I can describe and identify the types of discontinuities in a function. So go ahead, the opener here is an entire page. Go ahead and try this practice on your own. It is stuff from the past few sections. It's from 1.1.1.2 and 1.3. Okay, so time to check your answers. Let's see how you did. F of negative 1 is 2 times negative 1 squared minus 1. This is 1. 2 times 1 is 2 minus 1 is 1. So f of negative 1 is 1. Okay, next one. If f of x equals 7, find x, or what is x? So now I'm going to set f of x equal to 7. 7 equals 2x squared minus 1. So now I need to solve that. That only has an x squared in it, so I can solve it by square rooting, but I have to isolate it first. So I'm going to add 1 to both sides. 8 equals 2x squared. Divide by 2. I have 4 equals x squared. And then square root to solve. Don't forget to do plus or minus. So I have x is equal to positive and negative 2. Okay, next one. Find f of negative x. So we are plugging in negative x. So that's 2 times negative x squared and then minus 1. Remember on this, when you're plugging in negative x, your only job is to clean it up. So here I can clean this up. Negative x times negative x is positive x squared. So 2 times positive x squared is 2x squared and then minus 1. That is f of negative x. Next one, find f of a minus 3. So I'm plugging in a minus 3 and cleaning it up. So 2 times a minus 3 quantity squared minus 1. First thing I have to do is expand a minus 3 quantity squared, which is not a squared minus 9. You're going to lose a lot of points if you do that. It is a minus 3 times a minus 3, which is a squared minus 6a plus 9. So now I have 2 times this, which is a squared minus 12a plus 18, and then minus 1. So this is 2a squared minus 12a plus 17. F of a plus 1. Bless you. Right in my video, husband. Good job. It's okay. I'm going to continue. Does f represent a function? So is this a function? Okay, so in order to think about whether it's a function, I should probably highlight the whole thing right there. Okay, to think about whether it's a function, we have to think about what it is. What you can think about it two ways. You can think about what it looks like, or you can ask yourself, for every x value that I plug in, will it only give me one y value? So if I plug in any x value on the face of the earth, is it going to ever give me more than one answer? The answer is no, it will not. So therefore, it's a function. It's only going to give me one answer every time. Another way of thinking about it is that it is a parabola because it's a quadratic because there's x squared. And that passes the vertical line test. So yes, it is a function. What's the domain? If you look at the equation here, I asked myself, are there any restrictions? The answer is no, because there's no square roots and no denominators, so there are no restrictions. So the domain is all real numbers. Describe the end behavior using limit notation. So we already said that it is a parabola and it is upward facing. So the end behavior, the limit as x approaches negative infinity of the function, which his name was f of x, is equal to. So if you look at this end, as my x values get smaller, it's going up, so positive infinity. Limit as x approaches positive infinity of that function equals, as my x values are getting bigger and bigger, so are my y values, so infinity. Okay, now on to the new material. So first off, a continuous function. This graph right here is a continuous function. The graph of a continuous function has no breaks, gaps, or holes. So in other words, a function is continuous if you can trace it without lifting up your pencil. Okay, now I don't mean any like special tricks, like if this is what your graph looked like, there was a hole right here, and you're like, I can trace this without a pencil or without lifting up my pencil, watch. Like, oh, I can go like this. Like, that's not what I mean. Like, this is a hole. We put an actual open point right there to show the gap. But what it actually looks like is it looks like this, and then there's a gap right there. But we put the open point there so that you know, so you can physically see it with your eyes. Okay, so that's what a continuous function is. So what are types of discontinuities? So there are 3 types of discontinuities that you need to know. The first one is an infinite discontinuity. This graph has an infinite discontinuity. If you look, it's not continuous because I would have to pick up my pencil to draw it. Now, the way that I see this is I see that right here there's an asymptote. It's just not drawn in my graph, but there's an asymptote right here. So when you see an asymptote, that means that there is a discontinuity there, and the type of discontinuity, it's called an infinite discontinuity. So you should be using these words right here. Not calling it an asymptote discontinuity. It's infinite discontinuity. I like to think of it as this line goes on forever in this direction and forever in this direction. Infinite. This one has the easiest name, the best name. This type of discontinuity, so notice it's not continuous because I draw this piece and I have to pick up my pen to draw this piece. This type of discontinuity is called a jump discontinuity. So if you notice, your graph jumps from one y value to another y value. The last type of discontinuity is a removable discontinuity. So that is when you have just one point in the graph missing. So that if you colored in that point, the graph would be continuous. Okay, so that's called a removable. So if it wasn't removed from that, right, then it would be continuous. So removable. Now, I know that this is called a hole, but don't call it a hole discontinuity. It's called a removable discontinuity. Okay, so to check whether a function is continuous, it's called the continuity test. These are 3 things. It's a 3-step process. So first off, in order for a function to be continuous at the value of c, it has to satisfy the following conditions. F of x is defined at c. So it can't be undefined there. You can't say like, oh, it's undefined. If you think about it, if it was undefined, there'd be a hole there, okay? So then that means it's not continuous. The next thing that has to be true in order for it to be continuous is it approaches the same value from either side of c. So you have to, if you approach c from the left and you approach c from the right, it's the same value. Because if you think about it, if it's 2 different values, the limit doesn't exist. That means that there is a jump there or asymptote there. Finally, those 2 values have to be equal to each other. Okay, the 2 values that you just got for the last 2. So when we're doing our test here, and we're actually doing the test here, we're finding f of 2, making sure it's not undefined. We're going to find the limit as x approaches 2 and make sure it exists. And then those 2 things have to be the same thing. That means that it would be continuous. Okay, so let's give this a shot. Let's try this here. Now, once again, to match it up with example 1, 2, and 3, this is what we're doing in A, this is what we're doing in B, this is what we're doing in C. Okay, the graph is the same for all of these, so I'm just going to keep coming back to it. So this says find f of 2. So when x is 2, what is y? So I'm going to come to my graph. When x is 2, y is, it's really trying hard to be 3 there, mind you. It might have just moved a tad bit. All right, the next one. What is the limit as x approaches 2? So once again, here's 2. I'm going to approach 2 from the left. What y value am I approaching? I'm approaching 3. I'm going to approach 2 from the right. What y value am I approaching? I'm approaching 3. So since it's the same value, the limit is 3. Are those 2 things the same? Yes. What does this mean? It means that, I forgot to read the directions of the problem, but it means the directions were determine if the function is continuous at x equals 2. So it means that the function is continuous at x equals 2. F of x is continuous at x equals 2. So yeah, I did a really bad job of reading the directions here because I've done this problem so many times that I knew what it was asking me. Okay, let's actually read the directions for the next one, and let me delete what I drew on this. So the next one says, determine if the function is continuous at x equals 3. So I want to know if it's continuous at x equals 3. So if I want to draw, once again, a dashed line there just so I can have my eyes focus on it, I can. All right, so it says, find f of 3. So when x is 3, what is y? And you can see that there's nothing there, right? There's no point there. So this is undefined. All right, now we're going to find the limit as x approaches 3. So I'm going to approach 3 from the left. That is 4. I'm going to approach 3 from the right. That y value is 4. So the limit as x approaches 3 is 4. So now I have to ask myself, are these two things the same thing? Absolutely not. What does this mean? It means that it is not continuous there. So I want to know what kind of discontinuity is at 3. So let's look over and see what it is. If you can see right here, it's a hole. That means that if I replaced it, that it would be continuous. So that is a removable discontinuity. So removable discontinuity at x equals 3. Okay, next one. Determine if the function is continuous at 1. So now I'm going to look at the x value of 1. So 1's right here. Okay, so first one asks me, find f of 1. So when x is 1, what is y? When x is 1, what is y? So I see that this is a point. Remember, this is not a point, okay? So y is -5. All right, the next one says find the limit as x approaches 1. All right, so I'm going to approach 1 from the left. What y value am I approaching? -5. I'm going to approach 1 from the right. What y value am I approaching? -2. Those are two different y values, so the limit does not exist. These two are not equal, so that means that there's a discontinuity. What kind of discontinuity is this? If you look, it's a jump in the graph. It's a vertical jump. So there is a jump discontinuity. At x equals 1. All right, the very last one. Determine if the function is continuous at x equals -4. So I'm going to go ahead and erase all this. Or at least I tried to. -4, okay. All right, so -4. There's my asymptote. So clearly there is going to be a discontinuity here. It's an asymptote. Therefore, there's an infinite discontinuity, but we're still going to do the test. All right, find the limit, find f of -4. So when x is -4, what is y? There is no point at all, so this is undefined. Right here. Now we're going to find the limit as x approaches -4. So we're going to approach -4 from the left, and we're going to say what y value we're approaching. It's an arrow pointing downward, so that is -infinity. Oops, I only did one side. That's -infinity. And now I'm going to approach -4 from the right, and I can see that it's an arrow pointing upward, so that's positive infinity. Those are two different things. They're two different values, so therefore the limit does not exist. I shouldn't have called them a value, but they're two different things, concepts. Are those two equal? No, they are not. Undefined and does not exist do not mean that they would have to be the same value, right? Like 3 and 3 or -6 and -6. What does that mean? That means there's a discontinuity. What type of discontinuity? If you look, it's an asymptote. That's called an infinite discontinuity. So there is an infinite discontinuity at x equals -4. Okay, so that's it for section 1.3. Once again, as a reminder, you have 3 different types of discontinuities. An infinite discontinuity. This is an example of an infinite discontinuity. A jump discontinuity. That's an example of a jump discontinuity. It's always vertical also. And the last one is a removable discontinuity. That's an example of a removable discontinuity. All right, go ahead and get started.